Hello, I'm Chandranshu of DE Public School, Rupnanpur, Class 8. Today I will discuss about my research on the topic non-contact resistance I problem 6 for my submission to INYPT. First of all, I would like to discuss the problem statement as given. Uh, The problem statement states that the response of an LRC circuit driven by an AC source can be changed by inserting a non-magnetic or a ferromagnetic rod into an inductor coil. How can we obtain the magnetic and electric properties of the inserted rod from the circuit's responses? They are mentioning that uh, an LRC circuit is a circuit consisting of an inductor, a resistor, and a capacitor. And in our case, we connected them in series. How an LRC circuit, when a rod is inserted in the inductor coil of an LRC circuit, which is driven by an AC source, how does its magnetic and electric properties change? Here is a brief discussion of the various important terminologies. An LRC circuit is a circuit with an inductor, capacitor, and a resistor connected. And here, the one which I made is connected in series, as I mentioned. AC source which we used is the main AC supply of our home. We should have used the lower voltage and a higher frequency supply if possible, but nothing like that could be secured, and a voltage divider could not be used, as at the end of the day it would also end up taking a lot of resistance away from the LRC circuit, so the calculations would be hampered. The magnetic properties of a material generally help in classifying it into ferromagnetic or non-magnetic materials. Ferromagnetic materials are the materials which are easily attracted by a magnet and even retain slight magnetism when it is exposed to a field for long enough. Examples include pure and alloys of iron, cobalt, and nickel. And non-magnetic materials are the ones which generally do not get attracted to the magnets and do not retain magnetism for a long time, even though they do help slightly as a for electromagnets. For our experiment purposes, we used iron as the ferromagnetic material and aluminium as a non-magnetic material. Materials show many properties pertaining to electromagnetism. Among them include magnetic permeability, electric permittivity, conductivity, resistance, hysteresis, etc. But with the equipment that we had, all we could measure was whether the metal was ferromagnetic or not. With better equipment, though, magnetic permeability, and from that, via the 1 over c equals to square root of magnetic permeability into electric permeability by that formula, we can also derive the electric permittivity. What we did our methodology is first we collected the components as for the capacitor and the resistor, and we had to make the LRC inductor, as no inductor of a high enough inductance was found in the market. Using those components, we made an LRC circuit via joining them via the wires and taping the parts not where the voltage would not be measured, and just opening the both the ends of the inductor, as the voltage would be measured across them. By that, we measured the normal voltage when it is directly connected to the AC, and the voltage when it is when an aluminum and iron rod, both a thin and a thick iron rod, are inserted into it. A precautionary measure: the AC supply is very dangerous, so it must be, especially when like the one we made, so it must be taken with the care. Here are the basic values for our circuit. The voltage that we use, the capacitor and the resistance were given directly as per the mentioned in the casing. The inductance was measured, and the inductor's internal resistance was also measured. The inductor, we must mention, as it is not an ideal component like we use for our um, like we use for our theoretical models. It also has a included resistance, so the voltage we measure across the inductor is not just because of the inductance but also due to the resistance. So we must also take that into account during the theory. As per the theory part, the inductors and capacitors both change the phases of an AC circuit. Inductors try to prevent the changing of current, so they make the current lag behind the voltage, and the capacitors prevent the changing of voltage, so they make the voltage lag behind the current. Thus, they oppose each other's phase changes, and from that, by using the formulas for an AC circuit and solving the necessary equations, we can also find the net impedance that is given by a LRC circuit. Here is the basic formula for the main impedance as it is given by the LRC circuit. This is a textbook formula, so I did not show the derivation. Um, the impedance across the inductor is just the impedance caused by the ideal inductor and the resistance, and then the net um, voltage as measured across them. Now, when we insert the rod into it, the inductance value will change. So, the new voltage across it would just be found using the same formula, but replacing the L's with the L bars as the new inductance. Now, to find the factor by which the voltage increases, I just divided V bar by VL bar by VL, and by solving the basic equation, we just found this equation that is mentioned at the bottom of the page. Now, as you can see, it is a very complex equation, so it could not be solved directly. I did include its graph, and I will discuss about it. Here are the basic data of the rods that we used. Here is the voltage change as I found across it. For normal, the voltage is 0.8 volts, and when the aluminum rod is inserted, it is 0.8, and the iron rods make it 1.0, both of them. Now, a problem that is caused by the our instrument not being precise is we had to make an expected guess of the factor by which the inductance increases. Why? Here is the graph. Yes. So when since my multimeter does not have a small enough least count for the AC voltage, I had to give the ranges for the expected inductances. This is because this is the graph of the voltage change, and I have centered it. As you can see, when x equals 1, that is uh, L bar is equals to V bar. Um, Sorry, when V bar is equals to V, their factor is 1, their common factor is 1. So at that point, the normal, I set it to 0.8. Now, when the voltage changes, I cannot measure the accurate representation of the voltage. So all I can say is the voltage change is between 0.8 and 0.9 in case of the aluminum, and between 1.0 and 1.1 in case of the iron rod. So that is why I cannot give a perfect estimate of the factor by which the inductance increases due to the broad range as given by the blue and orange ranges. Thus, the expected factor by which it increases is given as 0 to 15% and 30 to 43%. Another problem which might be solved by better equipment is that the thin iron rod is going to change the voltage less than the thick iron rod, but because of the inaccuracy of my instruments, that no significant change could be found. So using more accurate instruments, we will be able to differentiate between them. The difference will not be much, since the most of the magnetic field lines pass through the center of the coil, and either way, even when they are thin, they will still pass through the center of the coil. But still, some difference will be there, and it is not that easy to find using our instruments. A few optimizations also I'd suggest to better the project, and these are generally instrument optimization. So if anybody helps get that, it will help produce enough data for our project. First is to in order First is to use a function generator instead of direct AC voltage as inductance, as the resistance caused by the inductance, impedance caused by the inductance varies proportionally to the frequency. So higher frequency would propound a similar increase in the voltage across the inductor, making it easier to find it. Second is using an oscilloscope to measure the voltage and the phase change, as it is more accurate. And the third one might use a lower inductance with a high enough power so it doesn't burn or at least melt as needed. That's it for my project. As we can see, all we can do for now is we can distinguish between the ferromagnetic and non-ferromagnetic materials, and performing the necessary optimizations uh, will also help us find the exact factor by which the inductance increases. Thank you. That is all.